So in this lecture series we shall learn about the theoretical aspects of truss structures and how we can design the trusses in practical in STAAD software. So I have seen many experienced engineers also they are not much comfortable with designing steel structures. So in this lecture I shall first of all teach you the theoretical aspects. So in the next lectures we shall learn how we can model the truss structure in a STAAD Pro and how we can model, analyze and design it. So in this lecture, first of all I shall teach you about the most theoretical concept, that is the right from ground zero, and then accordingly we shall learn much more technical concepts. So you can just Google the steel truss PDF. So I shall request you to download these two documents. That is, the number one is the detailed design of trusses by Unger Steel Group, and second one is the trusses by Instag. So Instag is basically an Indian organization that is doing the structural steel design work, and it is basically a standard organization, and this is basically a vendor which has released a detailed design of trusses. So first of all we shall open this detailed design of trusses option here. So here this PDF will open here. So first of all they had given the basic definition of trusses. Why trusses are different from the beams or different from the girders? Because once we are talking about the trusses, we are talking about the compression axial force and we are talking about the tension axial force. We are not talking about the bending moments here. So truss is basically essentially a triangulated system that is like this and interconnected structural elements, and it is also referred sometimes as open web girders, and all the connections are normally assumed to be pinned. Again the same concept, that is we do not allow any bending moment to develop at any particular node. So to avoid introduction of bending moment at any of the nodes, all the joints are pinned. An external force applied to the systems and reaction at the supports are generally applied at the nodes. So this is also a very important concept, that is when we are designing the trusses. There are two concepts: either we can apply uniformly distributed load over all this whole member, or we can calculate the equivalent nodal load and we shall apply the loads on all the nodes here. So they are generally applied at the nodes, but if required we can also apply in the form of uniformly distributed load, but again it is not recommended. So when all the members and applied forces are in the same plane, it can be called as 2D truss. When we are talking about in 3D dimension, then it's called a 3D truss. So what exactly is the use of truss in a single story building? So basically the most versatile use is to support the roofing arrangement. So it carries the roof load and it also provides the horizontal stability when we are providing wind girders at roof level, or when we are providing vertical bracing in the side walls or in the gable arrangement. So this is a simple portal trusses. So this truss is called a portal truss. These are the columns, and here you can see that the author has drawn two nodes here. So basically whatever axial forces and bending moments are here, they shall only be transferred to the columns. No bending moment shall be transferred from this truss to the column arrangement here. So this is also a very good planning here, that is they had tied all the trusses here from the top end, and similarly we shall also provide the purlins on the top to support the sheeting arrangement, and they had provided this vertical bracing and plan bracing on the top to take care of the horizontal forces here. So longitudinal stability is provided by the transverse wind girder and vertical cross bracing in the blue arrangement. So this longitudinal stability is provided by these transverse wind girders here and this vertical cross bracing. So here this arrangement is somewhat different. It is explaining that in second case, each vertical truss and two columns on which it spanned constitute a simple beam structure. So here we can see that basically this is a simple beam structure here, and the connection between truss and column does not resist the global bending moment, and the two column bases are pinned. So here we can see that these two column bases are pinned, but all these column bases are fixed here. And transverse restraint is necessary at the top level of the simple structure, and it is achieved by means of longitudinal wind girder that carries the transverse forces due to wind on the side of the wall as the braced cable walls. So in the next two lecture series, we shall also try to model this type of portal trusses and portal columns. But just as an understanding, it is very important that you read this whole paragraph again and again and try to understand how exactly the author is trying to balance the forces here. So further arrangement is shown here. So in this view, what exactly it is saying that the main trusses are drawn in blue, and the secondary trusses have a shorter span A, and this arrangement is called sawtooth roofing. So this type of roofing is drawn like this. And basically why we do provide this type of arrangement, this is also very important concept that you should understand. Most of the new beginners does not have any idea. There is a system called north light roofing. So you must be thinking that sun rises in the east and sets on the west. Then why we are talking about the north light roofing? Because north light roofing is the north is when we are considering the natural lighting from the north direction, it do remains in the day, because so that is why basically the purpose of this type of arrangement is that the light from the north side do gets inside the structure. So that is why it is called north light roof or north oriented windows. So different shapes of trusses can be seen here. This is called a simple Pratt truss, that is from the center. We are taking the directions like this, and when we are talking about the Warren truss, it is drawn like this. So in Pratt truss, diagonal members are in tension for gravity loads. Obviously when we are orienting all the columns along this side, so when this truss will try to deflect like this, all the members shall be in tension. And this type of arrangement is used where the gravity loading is predominant. And when we are designing a structure like this, we shall go for this type of arrangement when there is too much uplifting, such as in open buildings. So when we are talking about the closed buildings, we shall try to model the truss like this, and when we are talking about the open building, we shall try to support model the truss like this. So this is also a very important concept that you should understand, that in Pratt truss, when the members are going down here, this is good for gravity, but when the members are going up, this is good for the uplifting forces. And in Warren truss, diagonal members are obviously in tension and compression, and this type of truss is used for the horizontal truss of gantry or crane girders. After that, this X type. So if the diagonal members are designed to resist compression, the X truss is the superposition of two Warren trusses. Obviously when we are designed to superimpose these two trusses here, that is like this and like this, we will get X cross bracing here. And this is used mostly for the wind girders where the diagonal members are very long. And it is also possible to add secondary members in order to create intermediate loading points and limit the buckling length of members in compression. You must be thinking, what exactly is the buckling length of members in compression? So in the previous lectures you had learned much about the buckling analysis. So again, when the two ends are pinned, there is this maximum loading that can be applied on that particular member. So that is called the buckling load, and the maximum length for that particular loading is called the buckling length. So we can also provide this DO pitch truss here. This is called a north light roofing, that is north oriented windows. This is called a Fink truss. So here we can see that they have modeled this end truss in this range of 100 mm span. These are the base plates on which these trusses shall be lifted and installed. This is also called end truss, but the only difference is that when we are installing end trusses, the purlins are also end trusses. So basically you must be thinking that why we do need to go for this truss section, why we cannot just go with the I section, because in the same steel weight it is possible to get better performance in terms of resistance and stiffness with a truss rather than I sections. and difference is much more sensitive when we are considering about the longer spans. For example, let us say if we want to talk about the, let us say, span of 15 meter, or we should say 50 feet. So for 50 foot span, we can either go for an I section or either we can go for a truss. But the weight of the truss shall be much lower as compared to the weight of an I section. So that is the main sole reason why we go for the truss sections. But every advantage has a disadvantage also. So truss has higher fabrication timing requirements as compared to the simple I sections. So balance between the minimum weight and minimum cost depends on many conditions, that is equipment of the workshop, local cost of manufacturing, steel unit cost, etc. So truss generally gives an economic solution for spans over 20 or 25 meters. After that we can go for the this general geometries. So inclination can be in the range of 35 to 55 degree. Point load should only be applied at nodes. We should avoid applying UDL. And the section of the members, we can either go for this circular hollow section or rectangular hollow sections or simple angle sections, or called L sections. So section should be symmetrical for bending out of the vertical plane of the truss, and for member in compression, buckling resistance in vertical plane of the truss should be similar to that of the out of the plane. That is, the size should be square hollow sections. So for large member forces, it is a good solution to use cords having IPE, HEA or HEB section, because this is basically a Euro standard specifications. So that is why this language is being shown here. These are nothing but simple I sections that are being referred here. And diagonals can be from two angles. Type of connection. Obviously we had discussed in earlier also that connections can either be bolted or welded, but all those connections should not transfer any bending moment. They should only transfer the axial forces or shear forces. And for lateral stability, obviously we do need to provide lateral stability of the trusses also. So upper coordinates compression for gravity and bottom coordinates compression for uplift loading. So for portal trusses, each cord is partly in compression, partly in tension. So additional bracing may be necessary. So here we can see that this is one truss and this is another truss. So we had provided X cross bracing here between the two trusses. Plus, like this is also a theoretical concept that roof purlin also provide us the horizontal restraint. So I personally don't follow this, because sometimes it too happens that the purlin may not be much effective in the horizontal distribution. So that is why my approach is that I always provide the connection between the top cord and bottom cord between the two trusses. That I shall also explain in the next lectures. So design of wind girders, you can study that on your own. So they had also discussed about one example here. So basically, for this is the span of 45 meters. So in that 45 meter, they had provided a simple truss section here, and across the span, they had provided the purlins in the form of the trusses. So that is how they had worked out this 45 meter span. So here you can see that they had calculated the gravity loadings. Here they had calculated the uplifting loadings. So modeling can either be done in any of the software, let us say ETABS or SAP 2000 or STAAD or any local software that either your organization has license or you have license to that. And simplified, you can also calculate the forces in those truss sections manually, but obviously it is time taking. And coming back to the other file here, that is trusses by steel instruct here. So this is the file that has been provided by the instruct. So again, this is called a plain truss, this is called a space truss. This is a bracing in a multi-story building. This is again the plan bracing as well as the elevation bracing. This is the truss bridge, or we can also refer it as foot over bridge, or we also sometimes refer it as bowstring bridges. So trusses sections are, I must say, my personal favorite also, because they just zero the bending moment in the structures, and bending moment is a force that is very harmful for a structure. and harmful for the pocket also for the client. So if you if you provide a structure in which all the forces are either in compression or tension and bending moments are minimum, then the structure can be made much more economical and much more safer. So loadings, we can also go for the dead loading. In the dead load, we can consider dead load of claddings or dead load of purlins. Purlins are nothing but the members to support the sheeting. If you are not clear about the purlin, just Google it, because this is a very basic term and I expect you to know the basic definition of purlins. After that, self weight of trusses and weight of the bracings also. So further additional special dead loads such as truss supported hoist dead load, including special ducting or ventilator weight, or AHU can be hanged from the trusses, or solar panels can be installed on the top of the trusses. So any type of loadings can be there on the top of the trusses, but as a structural engineer, it's your duty to assess what type of loadings shall be occurring on the top in the life of that particular truss sections. After that, live load. Live load can be taken as per the non-accessible as per IS 875 that was released in the year 1987. But if you are referring to the American standards, you can refer AISC 07 that was released in the year 2016, or you can refer to EC1 if you are referring to European codes. And earthquake loads can also be applied, but they do not govern the design of the building. So that is what they had referred here, that earthquake load usually do not govern the design of the light industrial steel buildings. Wind is the force that governs the design of these structural steel buildings. So bridge trusses, analysis of trusses. So this is called a Pratt truss that we had referred already studied in the previous lecture. This is called a Howe truss, that is the members are going like this. This is called a Fink truss. Here you can see that there is the redundant member in the center is not here. This is called a fan truss, Fink fan truss, and mansard truss. So there are n number of trusses in the books of the structural steels, but it's up to you that you should decide that how you can what type of truss you need to install in which scenario. So this is just a simple floor girder. It is also called a joist as per the American standards. It is called a simple variant truss, lattice girder, K-type web, and diamond type web. This I had never seen in my professional life. These four are the one that I had seen the most. Trapezoidal trusses. Trapezoidal trusses are also that we had seen in this document here also, that when the span is very large, in that case this trapezoidal trusses are used. So it is saying that in case of very long span, trusses having trapezoidal configuration are the most stable and economical. This reduces the axial forces in the chord members adjacent to the supports. So they are usually used in the range of when the span is greater than 30 meters. And truss members. Truss members can be made with the help of these various types of structural sheet sections. Most common are these four, that is either we use for single angle or double angle or circular hollow section or rectangular hollow sections. When the span is somewhat higher, we either go with the channel or either we go with the I-shaped sections. And when the span is very high or very large, then we need to go with the built up sections, that is this double angle with the plate inside, this double channel with these batten plates, and double I with the top and bottom flange plates. And connections. Most of the railway bridges in India, US, UK, or various other countries, most of the railway bridges are made in the steel, and their connections is either by riveting or bolting. Welding is somewhat less desirable, as bolting and riveting is the most common connection type that I had personally seen in the railway bridges. So due to involved procedure and highly skilled riveting is not common these days, but when we are talking about the old structural steel bridges, riveting is always there. And high strength friction grip bolting and welding may have become more common. So nowadays the combination of high strength friction grip bolt, that is HSFG bolt, and welding, the connection is designed for the combination of these two types of connections. And longer span trusses can be prefabricated in segments by welding in shop, and these segments can be assembled by bolting or welding at the site. So this is a typical scenario of a connection here. So here you can see that simple gusset plate here, and on the top of the gusset plate 2 angle sections has been either been welded or bolted. And here you can see that the line of action of force shall come here, and line of action of this force shall come here at the CG of this particular angle here. So this is the common point at which these 3 forces shall meet. So it is not necessary that this member should go up to this distance here, or this member should basically touch this angle here. That is basically not required. So this is a typical bridge truss joint. So here also you can see that the sections are just welded on the this gusset plate, and line of action of this force shall come here. For this force shall come here, and for this force shall come here. So 1, 2, 3 and 4 forces shall be meeting at a particular point here. So again, it is not necessary that we should just we should join this member to this member. That is technically not required. So instability consideration should also be taken care. This is a simple guidelines for the slenderness ratio, that we should not make the structure much more cylindrical. And it is also a very good specific guideline that minimum angle section in the trusses should be 50-56, not less than that. And economy of trusses, how we can achieve that is, we should consider the method of fabrication, we should consider the availability of materials, erection techniques, method of connections, or either we need to go with rolled or fabricated sections. So these are the simple guidelines. Yeah, this is also a very good concept, that is composite truss. So if you are from like countries like US or UK or Dubai, so then in your college education you must have studied about the composite structural steel sections. So composite structural steel sections are like, we consider the transformed moment of inertia of a particular structural steel sections. So here you can see that on the top of this truss, with the help of this shear stud, we had provided a concrete deck slab. So it is just ingenious perception, or your experience perception, I must say, that what are your reviews on this type of arrangement here. Some people must be thinking that this is a load on this particular truss section here, but this is in addition to load, this shall also help in resisting the loads. How? By considering the transformed moment of inertia for this particular section here. So if you are not following my points, it's completely natural. I shall recommend you to study the composite design sections as per either the American standards AISC 360 or EC3, that is 0 codes. So using it as a part of compression member in truss system should be an economical proposition. So further, concrete can carry compression, and the structural steel and they are less vulnerable to buckling failures also. So concrete can easily carry the compression, whereas obviously it is weak in tension. So obviously the concrete and the structural steel, both the material are perfectly utilized in this type of arrangement here. So these are the type of various truss members here. So here you can see that 2 angles are joined by a rod, 2 angles are joined by a different angle, 2 T sections or double angle sections are again joined by a single angle, 2 angle sections on the top and bottom are again joined by 2 angle sections here. So World Trade Center was one of the largest application of the composite open web joist system. So joist, that I already explained in the previous lecture also. This is nothing but a joist, and American standard also has a separate design guidelines for the design of joist sections also. As far as I can remember, the code committee was named as SJI, the Steel Joist Institute, that specifically cover the design of the structural steel joist. So if you are interested in the design of the joist, you can just Google it. You shall also refer. You can also get some various ready-made practical examples of design of a structural steel and joist. So in World Trade Center, the system that was used was open web joist system in considering the composite sections, that is considering strength of the concrete as well as of the structural steel. Shear connectors are a very important part of the design. That is, these are the stud is the area that binds the concrete deck to the structural steel. So there's a separate design for the diameter of the stud, for the length of the stud, for the spacing of the stud, and for the number of studs in one plane. So effective concrete slab and pre-laminated design. In design forces, we do need to consider the various type of parameters like spacing or bending moments, etc. So restricting my lecture to the composite joist system, we should move to truss sections only. So after reading these two PDFs, I shall suggest you to go to this UAP, University of Asia Pacific website, that is uapbd.edu. There's this Dr. Iftikhar Anam. So he has provided a very good design guideline for designing of industrial trusses as per the American standards. So just left click here and this download this PDF. This is a very excellent document, I must say, if you want to and a very basic document also. So beginners shall not face any problem in following this document here. If required, you can also download the other documents also that are available free of cost on this website here. So he has solved a truss example as per the American standards, but the units are in foot and inches. So it's okay, the units are not an issue, but my approach is that you should have a solid understanding of the concepts that are involved in the steel truss design. So this is a simple truss section that we are considering here, and the height of this truss is approximately 24 inches. Here these are the purlins, and the end condition is that this is a roller and this is basically a pent connection here. So in the next lecture I shall explain you this whole PDF, how the author has calculated the forces and how we can model this steel truss in the STAAD Pro software. So in the previous lecture we have learned much about the theoretical aspects of the truss structures. Now in this lecture we shall try to model a practical truss, and we shall apply the dead load, live load and mid load on that particular truss structure, and I shall teach you how you can design a truss in the STAAD software. So in the previous lecture I requested you to download this PDF from a website that is available free of cost. So after opening this document, here you can see the simple cross section of the truss. So here you can see that basically these are the 6 spacings here, that is 1, 2, 3, 4, 5 and 6. The total span of this truss is approximately 120 foot and the total height of this truss is approximately 24 foot. Here you can see that this is the angle alpha, which shall be cross-referred when we shall do the design calculations, and these are the purlins that had been tied with the help of sag rods. So here you can see that this is the top view, and that is building plan. So these are the 3 trusses here, that is, this is a design truss 1, design truss 2 and design truss 3, and these are the purlins. So here you can see that the author is referred to as purlins at top, bottom cord bracing at bottom. So the purlins shall be tied at the top and the plan bracing shall be tied at the bottom of the trusses. So now this is simple math, that 6 into 20 foot is approximately 120 foot. So for those who are comfortable with SI units, I shall request you to do understand this lecture, because as an engineer you must be comfortable with both units, that is with the for FPS system also and metric SI system, and if possible MKS system also. So this is simple math, that is if you are comfortable in SI, you just need to multiply foot with 0.3 meter if you want to analyze what exactly is the distance in the meters. So here you can see that this is the 24 foot. So 24 into 0.3, that is approximately equal to 7.2 meters. So 7.2 meters is the height of the truss, and this 120 foot, that is 120 into 0.3, that is approximately 36 meter is this dimension from this point to this point. And if you talk about the supporting condition, so this is the roller here, that is only Fy can come here, and this is a hinge pin connection, so Fx and Fz reactions can come here. So this is statically determinate structures. So now the total span of the truss is approximately 120 foot, total height is 24 foot, spacing here you can see that this is the spacing, that is from this point to this point it is 30 foot, so that is approximately equal to 9 meters. Pitch angle is a very important concept that you do need to understand if you want to be conversion with PEB design, pre-engineered building designs, or truss design. Pitch angle alpha is this angle here, and if you are confident with your trigonometry skills, so this is just a simple math, that is this dimension is 24 foot and this dimension is 120 divided by 2, that is 60 foot. So if you want to calculate the slope of this truss here, so it is nothing but 24 divided by 60, that is 1 divided by 4, that is 1 in the slope is approximately 1 in 2.5 here. So if you want to calculate the angle, you can just consider this as tan alpha. So alpha is nothing but tan inverse of 24 foot divided by 60 foot. So that is what they had done, that is tan inverse of 24 by 60, that is the angle. This angle is approximately 21.8 degrees. And if you want to calculate, first of all we should calculate the dead load, live loads, and wind load on that particular truss structure. But before that, you should also be conversant with how you can model this type of truss structure in the STAAD software. So STAAD gives us an option to specifically tell it that we are working for space structure or truss structure or plane structure. If you remember my beginning lectures, so in that lecture I had already explained that there are 3 options in the STAAD software, that is either you can change the mode of STAAD to space, either you can change it to plane, or you can change it to truss. So those options are usually come at the beginning, but if you have already opened this window, you can just enter truss section here. So instead of space, if you enter the truss, then STAAD will specifically know that there shall be no out of plane forces. So that is also a like very important concept that you do need to understand. Sometimes it do happens that we do go for STAAD space, that is also not specifically wrong, but what happens is that out of plane forces also comes into picture in that case. So to avoid that and to make the truss much more economical also, we use the STAAD truss options. And as the author had used this units as foot and kilopounds, that is Kipps forces, so what we can enter here is unit as fit and KIPS, that is kilopounds. So we can just close this window here, and we can also enter the joint coordinates, that is 1, 0, 0 and 0. Now what happens is that basically it might happen that your whole interface is in metric SI. So if you press Ctrl C Ctrl V option, here you can see that the option are coming in meters, although there is an option to change the graphical display units here, but I shall not suggest you to do that because sometimes you may not be able to undo that. So to make the things easier or to make the things much more interesting, what we can do is that we can model the truss in the STAAD in the editor file also. So if your coordinate, if your origin is at this particular point here, the coordinate of this particular point is basically 60, and y is also 0 and z is also 0. So we can name it as 2, 60, 0, 0. So third point is 3, 120, 0 and 0. So let us close this editor file here, and if we want to see the distance here, it will again show in the meters. So it is approximately equal to 36 meters. So these coordinates are correct. After that, if we want to enter the coordinate of this particular point also, so it is nothing but x is 60, y is 24, and z is 0. So we enter here as 4 as 60, y as 24, and z as 0. So these are the 4 points that we had got by using the editor file option here. And after that, we can just model this truss here. After that, what we can do, we do need to model the secondary members also. After that, we can see that there are basically 3 parts here. So what we can do in our truss is that we can just left click here and left click on insert node, and we want 1 and 2 nodes in this particular truss structure. So we can left click on n equal to 2 here. So after that, if we see the arrangement here, so it is like this. So we can go to geometry, add beam by perpendicular intersection, and we can just model these secondary members here. So now this is somewhat similar to what has been drawn here, and after that we can just make the mirror image of this truss structure also. But before that, my usual practice is that I apply all the loading on this particular part and assign all the properties to these all members here on this side, and then I just mirror all the properties to this particular point here. But we can just make it an ideal case here. So symmetry, add beam by perpendicular intersection. So now that all the members have been drawn, after that we can go to the support, and here we can create the support. One is the fixed, but here it can only carry the Fy force. So as per this diagram, the roller support is here. So we can just assign the roller support here, and for this particular joint here we have pin connection here. So we can go to fixed but option, and we can go for Fx and Fz. So it cannot take Mx, My and Mz, it cannot take Fy, it can only take Fx and Fz. So that will make this truss a statically determinate structure, not statically indeterminate, as we have 3 number of degrees of freedom and 3 unknown reactions here. So in addition, what we can do is that we can also make it as indeterminate. So if required, we can make it determinate in the later on stages, but just to make it a practical case here, it cannot take this out of plane forces here. So we can release the Fz here. Yeah, now this is a correct practice that we are following here. And after that, now the basic arrangement has been drawn, basic supporting arrangement has also been given. After that, now we move on to the loading criteria here. So now under the loading criteria, what we can see here is that they had calculated a dead load first of all. So GI sheet is galvanized iron sheet roofing. So this is a simple sheet that weight is usually in the range of 2 pound per square foot and 2 psf. And after sulfate of Purlins is usually in the range of 1.5 psf. So total load comes out to be 3.5 psf, that is 2 plus 1.5. Purlins spacing SP. It can be approximately calculated as the length of top chord U1 U2, that is this part here. So that they had calculated in the range of 21 foot. So UDL on Purlins comes out to be approximately, so basically what they are doing is that they are calculating the purlin and sag rod sizes. So this whole calculation that we are seeing here is for the purlin design. So as I had discussed with you earlier also, that in this type of structure, please listen these few lines carefully. In this type of structure, we have one truss here, second truss here, and third truss here. As I had discussed earlier also, that we shall idealize this one truss here. So we shall calculate all the loading for this one truss, and we shall consider the effect of all these members, that is purlins and sag rods and tie rods, on the purlin, on this truss design, but we shall not model them. We shall design them individually. So that is what the author is doing here. That is, the author is designing the purlin separately. The author is designing the sag rod separately, and if required, he shall also design the top chord bracing separately. So this is also my approach in my day-to-day professional life, that if possible, I do not consider to model all of these elements in the STAAD. I only model the truss in the STAAD and do consider the effect or interference of the forces of the sag rods and purlins on the truss structure. So first of all, as per this sheet, we shall calculate the design of the purlins and sag rods. So purlin length is in the range of 30 foot. That is spacing of truss here. So if you are confident with the SI, the span is approximately 9 meters here. And on that purlin, let us see the purlin in the real life also. So here you can see that, and this is clearly showing all the arrangement here. So this is the purlin, and on the top of this purlin, the sheeting shall come. So, or you can see this picture also. So these are the purlins that we are seeing here. These are usually either of Z sections or channel sections, and on top of these purlins, sheeting is anchored. So it is not like if you model the truss, then everything is okay, but on the top of the trusses also, we do need to put the purlins, and on the top of those purlins, we need to anchor the sheeting arrangement. So this is the purlin that forms a connection between the GI sheeting on the top and the truss structure. So coming back to our calculation here, the GI sheet roofing can be considered as 2 PSF. Self weight of purlins can be considered 1.5 PSF. The total load comes out to be 3.5 PSF. Purlin spacing is in the range of 21.54 foot. So the UDL on purlins comes out to be approximately 3.5 into 21.5 foot. That is approximately 75.39 pound per foot. So WDLX is equal to WDL into sine alpha, that is 28 pound per foot, and WDLY is basically 70 pound per foot. So this sine alpha cos alpha is nothing but the horizontal and vertical component of this particular force here. So this is the section that is showing us the split components. That is here, the along the x it is 28 pound per foot, that is this value. The x-axis is the local x-axis of the purlin sections here, and this along this y-y axis it is 70 pound per foot, and this is the direction in the direction of the gravity, and this angle is 21.8. So this is simple trigonometry that the author is using here. So we can calculate the vertical and horizontal component for the dead loads, similarly for the wind loads also. So basic wind speed, we can consider it to be approximately 120 miles per hour. So for 120 miles per hour, as per the American standards AISC 07, the wind pressure formula is given as 0.00256 into V square. Here V is nothing but 120 miles per hour. So basic wind pressure comes out to be approximately 36.86 PSF. So this is the number one value that we have got here. After that, wind pressure for windward surface is different, for leeward surface is different. So it might be that you are listening all these terms for the first time. So in the first time, all these terms sound much difficult, may sound much difficult for you, But I shall request you to read the parallel literature also, and do repeat this lecture again and again, so that you may grasp how you can calculate the wind load as per the American standards. So coming back to this point, I shall give you a brief introduction of windward and leeward surface. So windward and leeward is like we had read all these about in our school also. So when the wind is flowing from this direction, let us suppose the wind is blowing from left to right. So in that case, this is the windward surface. And if this is the windward surface, this is the leeward surface. And wind is not always like wind always blow from this direction. Wind may also blow from this direction. So we do consider both the cases, and it may happen that when the wind is blowing from right to left, this is the windward surface and this is the leeward surface. So this was the basic concept of windward and leeward. So wind pressure for windward surface is minus 0.7 Q when the angle alpha is between 0 and 20. It is minus 0.07 alpha minus 2.1 into Q for 20 and 30 degree. Similarly for 30 and 60, and for 60 and 90. And wind pressure for leeward surface is nothing but minus 0.7 into Q for any value of alpha. So you may also remember these formulas. And pitch angle alpha that we had already calculated initially also, that is, it comes out to be 21.8 degree. That is between 20 and 30 degree case, that is this case. So when we are considering wind pressure for the windward surface, the equation that we need to consider is obviously this equation, that is 0.07 into alpha, that's 21.8, minus 2.1 into Q. Q is nothing but 36.86 psf. So wind pressure for windward surface comes out to be minus 21.16 psf. So this is just a simple math. I am repeating everything again. Basic wind speed we 120. After that, wind pressure we calculate 36.86 psf. Remember this term. After that, as per the codes, these are the values to calculate the windward and leeward surface wind pressure. For windward surface wind pressure, this is the equation that we need to follow. As per this equation, we put alpha equal to 21.8 and Q equal to 36.86. So P comes out to be 21.16 psf. Okay, after that, for leeward surface, it is irrespective of alpha, that is we need to use minus 0.7 into Q. So it comes out to be minus 25.8 psf. So UDL on windward surface. Now why do we need to calculate UDL? This is another important concept, and I have seen most of the new people getting confused in this concept. So I shall repeat 2 times this concept so that you may not get confused. Now this is units, this is the wind pressure. We do need to calculate the wind load. There's a difference between load and pressure. For pressure, unit is psf. For load, the unit is pound per foot. So now the thing is, we cannot apply 21.16 psf in your either STAAD calculations or manual calculations. So to simplify that this value here, what we need to consider is the spacing, and spacing of purlin is nothing but that we had already calculated here, that is SP is approximately 21.54 foot. That is the distance between this purlin and this purlin. So when wind is coming along this direction here, so it is the value that we had calculated it is in psf. So what we need to do is that we need to multiply the spacing between the 2 purlins, that is effective span area. I am repeating the term effective span area. This purlin shall contribute to resist the loading from 50% on this area and 50% on this area. When we cross this 50% path here, so after that the contribution comes out from this purlin. So this purlin shall resist the loading on this 50% area and this 50% area. So this is a very important concept that you do need to understand. So that is, the wind load is calculated in psf. We multiply the effective span of this purlin to calculate the UDL. So we multiply 21.16 into SP and 25.8 into SP to find out the UDL on windward surface as 455.72 pound per foot and on leeward surface as 555.85 pound per foot. So this is the same very simple calculations. And windward wind load, here you can see that along the local axis, it is showing us that the loading comes out to be 455.72 pound per foot, and on leeward surface it comes out to be 555.85 pound per foot. Now here we can see that when the wind is coming, leeward side wind load is quite high as compared to the windward surface. Now you must be thinking why we are talking about wind in the upward direction. When we are talking about the dead load, we are going down, and when we are talking about the wind, why all the forces are in up direction. So this is also a fluid mechanics concept, I must say. Most of you had studied the Bernoulli's theorem, and according to Bernoulli's theorem, everything wants to go from high pressure to low pressure region. So when the wind is blowing at a very high speed on the top, and on the bottom there is not much wind speed, so when the wind velocity is very high, the pressure becomes very low. If you remember the equation, I am not able to exactly recall the Bernoulli equation, but it was approximately P by rho plus Vg or something like that. So in that equation, P and V were the two variables, that is pressure and velocity. So when the pressure when the velocity becomes high, pressure becomes low, and when the pressure becomes high, velocity becomes low. So when the wind is blowing at very high speed on the top, the pressure becomes low, so everything goes from high pressure region to low pressure region, so it forms a suction on the top. So that is why if you see some cyclone videos on the internet or some hurricane videos on the internet, what exactly happens is that roof just blow out on the top. It is not like when the wind comes it crumbles to the bottom. Those failures are very irrelevant or very unpractical. It is always like under all the cases of wind failures are like the roof just got blown up on the top, or it just got the failed due to the very high suction pressure from the top. So this was the basic concept. That is why most of the times the wind forces are on the top. But sometimes it do happens that as per your internal pressure coefficient or external pressure coefficients, your wind pressure may go down also, but it all depends upon the design codes. So when we are talking about this leeward side and windward loading, so here we can see that combined UDL is coming out to be approximately along XS 28 pound per foot, that is for dead load, and 455 and 485.85 pound per foot. Now you must be thinking why we are considering this as 485.85 pound per foot, because basically 555.85 minus 70 comes out to be 485.85 pound per foot. So these are the UDLs in the X and Y direction. Now span of the purlin is 30 foot, so it is simply supported in Y direction, and we very well know that bending moment due to simply supported end conditions is WL square by 8. So here W is nothing but 54.66 into K dash, that is 655.90 K double dash at mid span. So now we do need to calculate the bending moment. So MXX bending moment is nothing but WL square by 8. So now when we put the values here, 485.85 into L square, that is 30 into 30 divided by 8, it comes out to be 54.66 KIPS. So this is nothing but pound per foot, but now the author has divided this by 1000 to comes out to be, here we need to divide it by 1000, so it comes out to 54.66 kilopounds. After that all the further equations are now basically into the inches here. So what the author had done is that he had multiplied this value by as 1 foot has 12 inches, so it has multiplied the value by 12, so it comes out to 655.9 KIPS inches. So the bending moment unit is kips inch. So similarly we can calculate the bending moment due to sag rods also. So now we can calculate the bending moment due to sag rods. So the equation for this type of bending moment is W into L square by 32. So we can just calculate it in this here. So Wx is nothing but this 28 into 30 divided by 32. So we can divide it by 1000 to calculate the value in kips, and right now the units is kips foot, so we can change it to inches by multiplying it by 12. So 9.45 kips inches is the bending moment units here. Now we can see that bending moment is coming in both the directions, that is mx also and my also. So absolute maximum tensile or compressive due to biaxial bending is given by this equation here, that is mxx divided by sxx plus myy divided by syy is the absolute maximum allowed tensile or compressive stress. Now mxx that we had calculated here, and now you must be thinking the units is in kips inches here, and here you can see that sxx is also in inches here. So the author had considered 3 sections here, and accordingly here he had shortlisted this section here, that is when we divide this 655.9 divided by 42 comes out to be approximately 15.61 plus 9.45 divided by 3.11. So 15.6 plus 3 comes out to be 18.66. So total sigma allowable then KSI is, if we are using this section, is 18.66, whereas allowable for when we are considering this FY is 36 KSI. 36 KSI is usually the yield strength of the structural steel that we use. So 0.66 into 36 comes out to be approximately 23.6. So 26.4 divided by 0.66. So the author had considered 40 KSI structural steel section. So 40 into 0.66 comes out to be 26.4 KSI. So this is the allowable bending stress, 26.4 KSI, and this is the bending stress that we had calculated by this equation, considering both the bending moment along both x and y direction and the moment of this modulus of section along both x and y direction. So C15 into 33.9. This term might be somewhat confusing for you, but this is a term that is used to denote a channel section. Channel section is the section that can be that is like this. So in this section, the height of this from this point to this point is 15 inches. So and the unit weight is 33.9 pound per foot. So if you can refer to this engineeringtoolbox.com website here. So here they had given the dimension for the C15 33.9. So the first number denotes the height in inches, and the second term denotes the weight, that is pound per foot, and approximately the depth is obviously 15. So when we consider that in mm, it comes out to be 381 mm. Width is 3.4. Width is from this point to this point here, so it is approximately 86.4, and the web thickness is 10.2 mm approximately, it is 0.4 inch. Sectional area is 9.96. Weight is 33.9 pound per foot. So accordingly they had given the elastic section modulus, that is 42 and 3.11, that the author had referred to as here. Similarly, if we want to study other sections also, so let us suppose if we want to go for the C6 into 13, so in that case the height of the web is 6 inches and the weight is approximately 13 pound per foot. I repeat, this is the web from this point to this point, and these are the two flanges. So steel sections in almost all the nomenclatures, whether you consider the British nomenclature for naming or you consider the American nomenclature for naming, the name itself denotes what exactly is the height of the section, and what exactly is the weight of that section. Similar is the case with the W sections also. So in the W, the nomenclature is that for American standards, they write the height of the section and the weight in pound per foot. So moment of inertia and elastic section modulus is nothing but z here. So z is I divided by y. So all these are the basic concepts of the materials that I consider that you already know. So now we had designed the purlins here. So the Purlin C1533.9 is considered as the final, considering all the loading that has been applied on the truss section as per the 120 miles per hour wind pressure. Now, what exactly is the unit weight is 33.9 per pound per foot when we divide it with the 21.54 number. 21.54 is nothing but this number here. So this is the spacing. So when we divide the UDL with the spacing, it again comes out to be in PSF. So initially we had considered the self weight of purlin as 1.5 PSF as per this term here. So this is the standard practice that we use when we are designing the structural steel sections manually, that we do consider the self weight of the structure also when we are doing the manual hand calculations. And at the end of the calculation, we do make sure that whatever section we have finalized, for example in this case we had finalized this section, the considered unit weight and the final unit weight, there should not be of much difference here. So in this case you can see that both the assumed unit weight, that is 1.5 PSF, and calculated unit weight is almost approximately equal to same. So design of purlin section is now closed with the final section as C1533.9. Now how exactly we can design the sag rods? So most of you must be getting confused with the sag rods also. So sag rods are also a very basic tool that we use to make the purlins stronger along the minor directions also. So here you can see that these are the Z-shaped purlins here, and from those purlins we have tied the sag rods here. So this is a typical example of a sag rod. Here the diameter is 16 mm, and we are tying these both purlins with the help of this sag rod to make the section strong along the minor direction also. So in the major direction, the section is already strong due to the distribution of the structural steel, but the sections are usually weak along the minor direction. So by tying the two purlins along the minor direction also, we make the structural sections strong. So that is why we do design the sag rod. Usually the sag rod diameter is either of 16 mm or 20 mm. So maximum actual force in the sag rod is 5 by 8 into WTLX into X. So 5 by 8 at 20 approximately comes out to be 525 pounds, that is 0.525 kips. So minimum size of sag rods is 3 by 8 inches, allowing 1 by 16 inches for reduction of bolt threads. If you are conversion with AISC 360, so in that case, as per the diameter, the code gives us some reduction in the diameters. So if it is less than, I think 0.5 inches or something like that, when we do need to consider 1 by 16 inches reduction. So the rod area is nothing but 3 by 8 inch minus 1 by 16, that is this reduction, pi d square by 4, that is 0.077 inches square. So maximum stress, here we can check that it is 0.525 kips divided by 0.007 inches square. So it comes out to be 6.8 for KSI, whereas the allowable obviously this 20 KSI. Now the sag rod can be considered as 3 by 8 inches diameter, and weight of sag rod and bracing should be within the assumed limit of 1 PSF, that is pound per square foot. So here we can see that the assumption of 1 PSF can be taken. So this was the assumption that we had initially considered. Sag rods plus bracing should comes out in the range of 1 PSF. Now in the next lecture we shall learn how we can calculate the dead load, wind load, and how we can apply the loading in the STAAD software. So in this lecture we shall learn how we can calculate dead loads, how we can calculate the wind load, and how we can apply those loading in the STAAD, and then how we can ultimately analyze and design that particular truss. So now what we can do is that we can calculate the dead loads here. So dead load, as we had discussed earlier, that is we shall consider 2 plus 1.5 plus 1, that is 4.5 psf, that is pound per square foot. So 2 plus 1.5 is nothing but 2 is the dead load due to roofing, 1 is the dead load due to sag rod plus bracing, and 1.5 is the dead load due to purlins. So the total dead load comes out to be 4.5 psf. Purlin spacing is 21.54 and truss spacing is 30 foot. So concentrated roof loads on the truss joint can be calculated by 4.5, that is this value, into the spacing of purlins into the spacing of truss divided by 1000 to calculate that in kips. So it comes out to be 2.91. Now as we are not designing it manually, and we are designing it with the help of STAAD software, that is this truss section here we are designing it in STAAD. So we do not need to consider the self weight, because STAAD itself has a command to consider the self weight also. So now we shall apply the roof loading on the top as 2.91 kips. So we can go to the load and definition here. Here we can enter the value as, first of all, dead load. After that we can consider live loading also, and then we can consider the wind loading also. So wind load X we can consider, and wind load minus X we can consider. So under the dead load we can go for the self weight option, that is Y we can consider as minus 1.05. We can left click on assign to view. After that we can add dead load with the nodal load option here. We can enter minus 2.91 kips value. So here we can see that automatically the units are in KIP. So we can left click on add here, and then we can select all the nodes here, and the loading on all these nodes shall be 2.91. but for this end node, as I had explained you earlier also, that the span is 50% of this. So we can go with nodal load as minus 1.46. So left click on add here, and then we can just assign to selected nodes and gears. So now all the loading has been applied for the dead load. After that we can assess the live load also. So live load, as this author has not considered, so we can consider live load in the range of 15 to 20 psf. So if the slope is greater than 4:12, then we do need to consider this 15 psf, and when the roofing is in either flat or the slope is in the range of 4:12, so in that case we do need to consider 20 psf. So in our case we can go with the lesser value, so we can go ahead with 15 psf force. So now when we are considering this 15 psf force here, so in that case we do need to consider 15 into this SP into ST divided by 1000. So that value comes out to be approximately 15 into SP is 21.54 into ST is 30 divided by 1000, and this value comes out to be approximately 9.7 kips forces. So we can go to the live load option here, and we can enter nodal load as minus 9.7, and 50% of that for the end condition we can enter minus 4.85. So we can select all of these nodes here, and we can select this node here. So now the dead loads and live loads are covered. After that, the major thing that we do need to consider is the wind load option here. So wind load we can also check as per the calculations. The value of wind load has already been assessed when we were designing the purlins. So in that case, the windward surface, the loading was coming out to be 21.16, and on the leeward surface the loading was coming out to be 25.8 psf. Now when we are considering the concentrated load on the windward surface, obviously we need to multiply SP into ST divided by 1000, the spacing of Purlin into spacing of truss divided by 1000 to calculate the value in Gibbs. So on the windward surface it is 13.67 and 50% here, that is 6.84 and 6.84. So how we can apply the loading along this direction, that is also somewhat difficult in the STAAD software. So that is why we do need to apply the components, that is horizontal components and vertical components in that. So now either we can apply the basically the thing is that when we apply the nodal loads in the STAAD, it can only goes in the up direction. So one usual practice is that we can split the components into cos theta and sin theta, and then accordingly we can apply it. So in all the cases what we need to do is that as this angle is 21.8 degree, so this angle here is also 21.8 degree. So accordingly we need to calculate the horizontal components and vertical components to calculate the this nodal loading here. Or what we can do to in order to save time is that we can also apply a UDL here. So although that is not a desirable approach, I must say, but basically fundamentally it is also correct. So what we can do is that here the author has also multiplied this 21.16 psf with the spacing of Purlins. So what we need to do here is that we just need to multiply 21.16 into 20, that is the spacing of the trusses. ST value is 30 foot. So what we need to do here is that 21.16 into 30, that needs to be divided by 1000. So the UDL value is coming out to be approximately 0.6348. So the UDL is coming out to be approximately 0.635 kips per foot. So we can go to the wind load X here, and we can go to the member loading option here. We can select Y local here, and as the unit is kilo pascal per foot, so we can apply 0.6348 for the windward here. And for the leeward side, what we do need to consider is that 25.8 into 30 divided by 1000. So this UDL is coming out to be approximately 0.774. That is on the leeward side we do need to apply 0.774. So here we can select all these members here, and then we can click assign selected beams and gas. Similarly for the leeward side we can just apply the loading here. So now all the basic math or trigonometry, so whatever we do need to consider for this, that is we do need to consider the horizontal component, vertical component, and 50% for this, automatically the STAAD will calculate it. And there's this one more thing that notice that I had applied the loading in the local Y, not on the global Y. So when I change it to global Y, what happens is that here you can see that the loading acts against the direction of gravity, not against the direction of the member. So that is why we do need to consider the Y local here, not the global Y direction. Similarly, we do need to reverse the directions also for windward minus X, that is windward will become leeward and leeward will become windward. So we do need to enter 0.6348 for Y local and 0.774. So in this case it was windward, and in this case it is windward. And here we can apply the loading along the leeward direction. So now all the dead load, live load and wheel loading has been applied to this truss section here, and now we are done with the application of the wind load also. So after that we can consider the load combinations also. So load combinations we can enter as per the American standard. So what we can do here, we left click on load cases details, We can go to auto load combinations. Here we can enter AISC and general. Left click on generate loading option. So all these are the various types of the loading that has been auto generated with the help of this option here. So we can left click on add here, and after that we can go to the property sections. Under the property sections, the author has predicted that bottom chord members are in the range of 5 by 5 by 5.8, and top chord members are in the range of 4 by 4 by 3 by 4 inches, and web members are coming out to be 4 by 4 by 5.8, 5 by 8 inches. So 5 by 5 means that this height is length is 5 inches, this length is also 5 inches, and thickness is 5 by 8 inches. So we can American, and here we can left click on angle here, and here 5 by 5 means 125 mm angle. So we can left click on this 120 section here, and let us check the thickness. 5 by 8 into 25.4, 5 by 8 into 25.4 is the thickness. So the thickness is approximately 16 mm. So we can left click on this, select this 120 120 18 angle, and then left click on add here. We can left click on LD also. So this is a double angle section, so left click on add here, delete this section here. The author has predicted this for the bottom chord. So this is the bottom chord here, and for the top chord member, the author has predicted that the size is approximately 4 by 4 by 3 by 4. So left click on section database again. 3 by 4 inches means 0.75 into 25.4, approximately 19 mm. So left click on angle here, and we can select 100 by 100 by 18 or 19. So we can select 100 by 100 by 20 here. Select long leg back to back double angle here. So select all these members here, and for the web members, what we can consider is 100 by 100 by 5 by 8 inches. So, or what we can do is that we can also increase the size of these members here. So we can go to the angle here, and we can select 100 by 100 by 12 long leg back to back double angle. This is basically a redundant member here, but there is some force in this member also. So now the properties have been assigned. Specification we don't really need to provide when we are talking about this STAAD truss option. Supporting we had already defined. Loading and definition and load combination we had already provided. After that we need to go to the analysis, and after that we do need to apply the load list command also. So before that we need to go to the design steel. Here we need to select AISC ASD, and here we need to select the defined parameters. Under the defined parameters we can select FYLD command. FYLD is in kips per foot square. So we can select yield strength of steel as 5184, and we need to check the other specifications also. Yield strength we is already selected. Ultimate tensile strength we can also select. KY and KZ we can go for this 0.85 as both the ends are pinned. Only for the intermediate members, not for the end members. And LY we can select it as the LY we can select whenever we are providing the break here. So wherever there are members here, we shall break the member along the minor direction also. So that is why we don't really need to provide LY. This is a rolled section type. So after that we can left click on assign to view. KY and KZ we can apply to all of these members here. Similarly, we can apply kzer to all of these members here, as both the ends are pinned. So that is the basic concept here, and all the sections are hot rolled, so that is why we selected HTTP as one. We can go to commands and left click on check code and take off. So we can left click on assign to view again. We can check the loading and definition criteria here, and we do need to apply the load list command also. So we can go to perform analysis and load list 5 to 14. After that, we can analyze the structure. So we can check the design results here. So here we can see that the utilization ratio is very low here. That is, the loading is very less here, and as predicted, the bottom member is always in the tension, so that is what they had predicted here. And here also this is again tension. So we can also decrease the size of these members here. So if we want to decrease the size of this member here too, L 100-112 and long leg back to back double angle. Similarly, we can decrease it to L 80-88 and long leg back to back double angle. Again, we can analyze the structure. And now again we can see that the ratio here is very low, but for this member the ratio is somewhat higher here, so that is, it is going up to 63% utilization ratio. So if required, we can again decrease the size of this member here. But overall, I hope the things are now clear to you, that how you can model the truss and how you can apply the loading. After that, what we can see is that we can go to the post processing here, and we can check the maximum deflection here. So the maximum deflection is coming out here approximately 17 mm in the bottom direction. And you must notice that when we are left clicking here, my and mz is by default 0. There are no chance that there can be even 0.01 value of my or mz, because right now we are working in STAAD truss and not STAAD space. So this thing is clear to you. After that, we can check the reactions also. So here we can see that only vertical reactions are coming here under the case of dead load, and obviously when we will apply wind load, in this case we are getting two reactions here, that is x and y, and here also we are getting this direction along y. So there are three reactions and three unknowns and three reactions. So it is basically statically determinate structure here. So if we want to see the bending or tension compression values also, so we can left click on this labels, scales, apply immediately. Here we can increase the capacity of this axial forces. And if we want to see the values also here, that is, we want to check what exactly are the value for the different types of forces for different types of load and load combinations. What we need to do is that we need to go to results, view value, and beam results. Here we need to select axial at ends, and we need to left click on annotate here. So now we can see all the axial values. So everything is, I think, clear to you, that you can see. Here also you must be wondering why there are two colors in this profile here. One is the red and one is blue. Red means tension and blue means compression. When we go to this label sections here, and we can check this loads and result. Here it means that the red means compression and blue means tension, but that is basically the force. So when we are left clicking here, you can see that this is basically showing as compression, and this is the one that is showing as tension. Obviously when this will try to deflect here, obviously all these members shall come under tension, and these members shall come under compression, and again these members shall come under the tension forces. So this was just a basic exercise to access that how you can design the truss sections. And what if we, instead of space truss, we enter the space? Let us just run the analysis here, and after that let us check the results. Here we can see that there are 3 warnings and 3 nodes here. So that is the basic difference, that when we are doing the analysis in the STAAD space, you will get the instability errors. So when we will open the file here, you will see that it is showing us the instability, because we have not provided any restraint along this direction. And here also you can see that MZ value has also become visible here. So all those members that were getting passed when we were accessing it for STAAD space, for STAAD truss, are now getting failed here as when we had assigned it to as STAAD space. So that is the difference between truss and space. So I will always suggest, when we are doing the planar analysis of any truss section, we should always go for STAAD truss. But basically the problem is that why this bending moment value is coming is because we had applied the UDL on these members. So when we were doing the STAAD truss analysis, at the back end the STAAD was calculating the nodal loads by itself. So that is the basic difference. So I shall always suggest that always enter the STAAD truss option here, and do check the behavior and do check the results. So all the things have been assigned. After that we can design the bracings also. So bracings and connections, the author has given various simple diagrams here, that this is a gusset plate, and on this gusset plate they had provided this 2 angle sections here, and here they had provided the welding, that is 1/4 and 21 inches long. After that the author has also designed for the anchorage and support also, that is when we do need to design the base plates at the end also. So this is the anchorage that they had designed. So they had taken the 0.5 inch thick base plate of 7 inches by 14 inches size, and 6 inches anchorage has been considered here. This is a concrete pedestal. So this is a typical roller support that the author has shown here. And if we see the basic design of the anchorage and end support, they had considered the tensile force, compressive force, and shear forces. So the maximum tensile stress in column is 0.146 KSI when we are considering the masonry columns. So here he had also designed the welding also, that is 0.7070 is the simple law for considering the thickness of the welding, that is we decrease the thickness of welding by 0.707 times. So if the thickness of gusset plate is 0.25 inches, and thickness of weld is also 0.25 inches, so length of the weld is calculated approximately with the help of this formula here. And now our allowable shear stress formula is 0.3 into Fy as per AISC. So here you can see that these are the 2 trusses that we had already designed. After that we can join all the bottom chords. So that is why we have not taken any LY in the truss sections here. If we are not providing any this one members, that is 1, 2, 3, 4 and 5 members, we are not providing, then in that case we do need to provide LYS from this point to this point. And all the members and all the ties we are joining, in addition bracings we are also joining. So in that case we don't really need to assign the LY. So I hope the things are now clear to you, that you can approach truss designing confidently from your at your own end also. So do study some books on the structural steel design also, and do study about the truss behaviors, how truss structures are much more simpler as compared to the bending structures. So with this closing lecture, I close this lecture on the truss structure analysis. So in the next lecture series, we shall learn how we can design the 3D trusses.